Previously, we used contingency tables to look for associations between discrete variables. We said that if there was an association between two variables, knowing information about one variable, such as the child's age, makes certain values of the other variable more likely, like the child's height. As an example, we looked at political affiliation by employee type. We found that the distribution of employees among different political parties was different for executives and production workers. That is, there was an association between political affiliation and employee type. If you look at executives as opposed to production workers, it changes the proportion of Democrats and Republicans. To look for an association in the contingency table, we converted the frequencies, that is, the number of people in each category, to conditional proportions. Instead of looking at the proportion of all workers that were Democrats, we looked at the proportion of just the executives who were Democrats, and the proportion of just the production workers who were Democrats. These are the conditional proportions, proportions only out of the part of the group that matches some criterion. Here, the criterion is based on employee type. If the conditional proportions were the same across different levels of the explanatory variable, that is, if employee type didn't make a difference with respect to political affiliation, we said that the variables were independent, no association. Today, we're going to extend this from proportions to probabilities. That is, if two random variables are associated, then knowing information about one variable changes the conditional probability distribution of the other. What's the difference between a proportion and a probability? A proportion refers to the makeup of an actual group. For example, the proportion of students who live out of state, based on the records in the registrar's office. A probability refers to how plausible we think a given statement is. For example, how plausible it is that this student that I just met lives out of state. A proportion refers to real things. A probability is an idealized quantity, a model or theory about the world. In one sense, all probabilities are conditional probabilities. We talk about the probability of a particular outcome X, given our background information B. How plausible the outcome is depends on, or is conditional on, our background information. For example, we can talk about the probability that it will rain today, given that there are heavy clouds in the sky. The plausibility of rain today depends on, or is conditional on, whether there are heavy clouds in the sky. If our background information changes, then the plausibility of each outcome changes as well. For example, if the sky suddenly clears, the plausibility of rain today decreases. In general, getting new information changes how plausible each outcome is. Let's look at an example. Suppose you and your friends are trying to decide where to go out to dinner tonight. Each one of you wants to go somewhere different, so you decide to choose fairly by drawing out of a hat. Each of you puts the name of your restaurant on a scrap of paper from the recycle bin, but it so happens that some of the scraps of paper were white, the restaurants Root Down, Linger, and New Saigon, and a couple of them were green, Watercourse and Steubens. Before pulling out a name from the hat, since you don't have any reason to believe that one name will be more plausible than another, the 5 outcomes follow a uniform probability distribution. That is, the probability of Root Down, given that there are 5 names in the hat, is the same as the probability of Watercourse, given that there are 5 names in the hat, and so forth. They're all 1/5. But, just as your friend is pulling the winning slip of paper from the hat, you happen to catch a glimpse that the paper was green. Now you have new information. Given that the winning restaurant was on a green slip of paper, is it at all plausible that you'll be eating at Root Down, Linger, or New Saigon? No, those were written on white slips of paper. The probability distribution conditional on this new information is different from the original probability distribution. The probability of eating at Root Down, given that there were 5 names in the hat and the winner was green, is 0. And the probability of eating at Watercourse, given that there were 5 names in the hat and the winner is green, is 1/2. Once we received the new information that the winner was on green paper, the restaurants on white paper were no longer relevant, so we could restrict our sample space to just those restaurants that were written on green paper. Just as a conditional proportion is a proportion restricted to just part of the group, we can think of conditional probabilities as probabilities that are based on a restricted sample space. Let's look at another example. Suppose you have a bag with a bunch of marbles in it. Some of the marbles are striped and the rest have dots on them. Some of the marbles are colored red and the rest are colored blue. Maybe it looks something like this. Say you have 4 blue striped marbles and 6 blue dotted marbles, 3 red striped marbles, and 7 red dotted marbles. This contingency table treats the marbles as a group of real objects. Now, instead of thinking of the marbles as a group of objects, Let's think about the random phenomenon of shaking up the bag and drawing out a marble randomly without looking in the bag. The contents of the bag form the entire sample space. What's the probability that a marble drawn out randomly is dotted? Well, there are 13 dotted marbles, and there are 20 marbles total. The chance of selecting any given marble is the same across all the marbles, so we can just take the number of dotted marbles and divide it by the total number of marbles. So we take 13 over 20 and get 65%. The probability of drawing out a dotted marble is 65%. But suppose we're playing a game in which you have to guess whether the marble I've just drawn out is striped or dotted, and I decide to give you a hint. I tell you that the marble is blue. Does that change the probability that it's dotted? Yes, since the proportion of dotted or striped marbles is different depending on the color. For blue marbles, there are more striped than dotted, but for red marbles, there are more dotted than striped. If you know that the marble I drew is blue, then it's as if you've restricted the sample space. Because you know that the marble is blue, you know that it can't be any of the red marbles. It's as if they don't exist. Now, in this new bag of blue marbles, what's the probability that the marble is dotted? Well, there are 6 dotted blue marbles and 10 blue marbles total, so 6 over 10 is 60%. The probability that the marble is dotted, given that it's a blue marble, is 60%. The conditional probability is the probability that one event happens given that some other event has occurred. In mathematical notation, we write it like this: the probability of the event A given that the event B has occurred. And it's calculated as the probability that A and B both occur divided by the probability that B occurs, irrespective of whether A occurs. So in our example, A was that a marble was dotted, and B was that the marble was blue. So we found the probability that the marble was dotted, given that the probability was blue. Let's see how this formula works with that example. The probability that the marble was blue was 10 out of 20, or 50%. And the probability that a marble was dotted and blue was 6 out of 20, or 30%. So we can find the probability that the marble was dotted given that it was blue, that is to say, the probability that the marble was dotted only considering the blue marbles. This conditional probability is calculated by taking the probability that it was dotted and blue and dividing by the probability that it was blue. So we take 30% divided by 50% and we get 60%, which is the same answer that we got before. Or we could look at our employees and political affiliations. Instead of thinking of this sample of employees and political affiliations, let's instead think about the random process of selecting a random employee and seeing what their employee type is and political affiliation is. If we wanted to find the probability that an employee was Democrat, given that the employee is an executive, then we take the probability that an employee is both a Democrat and an executive and divide by the probability that the employee is an executive. Well, the probability that the employee is a Democrat and an executive is 5 out of 140, that's 3.6%. And the probability that an employee is an executive is 48 out of 140, that's 34.3%. So we take the 3.6% and divide by 34.3%, and we get 10%, which is what we found before. The thing you're conditioning on, that is the event to the right of the vertical bar, becomes the new sample space. It's as if all of the outcomes that aren't in that event no longer exist, just like those red marbles. In the equation for conditional probability, the event being conditioned on is in the denominator, just like the size of the sample space was in the denominator when we were computing the probability of an event with equally likely outcomes. The outcomes of the event become the new or the effective sample space for the conditional probability. When you're trying to figure out what's being conditioned on in a word problem, ask yourself, what's my new sample space? Or to what subgroup am I restricting myself? In the example with the marbles, we were restricting ourselves to just the blue marbles. In the example with the employees, we were restricting ourselves just to the executives. Note that it is not necessarily the case that the probability of A given B equals the probability of B given A. We can see this if we look at how the two conditional probabilities are calculated. The probability of A given B on the left here is the probability of A and B divided by the probability of A. And the probability of B given A on the right is the probability of A and B divided by the probability of B. Notice in these two fractions, the numerators are the same, but the denominators are different. If the probability of A is not the same as the probability of B, then these two conditional probabilities will be different. You can see this pretty clearly if we think about the example with the marbles. The probability that a marble is dotted given that it's blue is not the same as the probability that the marble is blue given that it is dotted. Since something different is being conditioned on, the sample space for the conditional probabilities are different. In the bag on the left, you see only blue marbles, some of which are dotted and some of which are striped. In the bag on the right, you see both blue and red marbles, all of which are dotted. Finding the proportion of dotted marbles in the left bag or the proportion of blue marbles in the right bag is not going to be the same, except in very special circumstances. Conditional probabilities are incredibly useful for finding the probability of complex combinations of outcomes due to something called the multiplication rule. The multiplication rule says that the probability of A and B is equal to the probability of A given B times the probability of B. Let's see how this formula works using our marble example. We know that the probability of a marble being blue is 50%, and the probability of a marble being dotted given that it's blue is 60%. So the probability that a marble is dotted and blue is equal to the product of those two probabilities, the conditional probability that the marble is dotted given that it's blue, and the marginal probability that the marble is blue no matter whether it's dotted or striped. So we take 50% and 60% and multiply them, and we get 30%, which is what we found before when we took the number of blue dotted marbles, 6, and divided by the total number of marbles, 20, which gives 30%. Or we could look at the employee type and political affiliation example. If we know that the probability of being a Democrat given that you're an executive is 10.5%, and the probability that you're an executive is 34.3%, then we can find the probability that you are a Democrat and an executive by taking the conditional probability that you're a Democrat given that you're an executive and multiplying by the probability that you're an executive. So we take the 10.5% and multiply it by 34.3%, and that gives us 3.6%, which is the same as if we took the number of employees who were executives and Democrats, 5, and divided by the total number of employees, 140. So what does the conditional probability look like for events that are independent? Well, if A and B are independent, then the probability of A given B is just going to be the same as the marginal probability of A. That is to say, if A and B are independent, then your value of B makes no difference for your value of A. This was the example table that we used to show what the conditional distributions of political affiliation would look like if employee type and political affiliation were independent. We saw that the proportion of Democrats was the same no matter whether you were an executive or a production worker. So in this example, the probability of being a Democrat given that you're an executive is 68%. But the probability of being a Democrat irrespective of whether you're an executive or a production worker is also 68%. They're the same because whether you're an executive or a production worker doesn't make any difference for whether you're a Democrat because the two variables are independent. So the conditional probability that you're a Democrat given that you're an executive is equal to the marginal probability that you're a Democrat. So why would we care about conditional probabilities? Well, one reason is that conditional probabilities play an important role in understanding the accuracy of medical testing. We have all kinds of medical tests available, but no test is perfectly accurate. Sometimes they show a positive result when really there's nothing there, or they show a negative result when there really is something there. There are two different ways of thinking about accuracy, each with its own challenges. Getting a positive result when there's really nothing there can cause unnecessary head or heartaches, as well as potentially wasteful medical treatment for something that really isn't a problem. Or getting a negative result when something really is wrong means that potentially serious medical conditions may go undiagnosed, possibly leading to serious complications later on that could have been handled easily before the condition progressed. We have names for each of these types of accuracy. Sensitivity is the probability of testing positive given that the condition is true. That is, of all of the people who actually have the disease, how many of them will the test actually show have the disease with a positive test result? The specificity is the probability of testing negative given that the condition is not true. So instead of thinking about all the people who have the disease, now we're thinking about all the people who don't have the disease. How many of them does the test accurately show don't have the disease with a negative test result? Those are the accurate cases when the test gets it right. We can also talk about the mistakes that the test makes. The false positive rate is the probability of testing positive given that the condition is not true. That is, of all of those people who didn't have the disease, how many of them did the test actually come back positive, incorrectly suggesting that they had the disease? And similarly, we have the false negative rate. This is the probability of testing negative given that the condition really is true. So of all those people that had the disease, how many of them came back with a negative test result? The test didn't actually catch the fact that they had the disease. The false positive and false negative rates are really just the flip side of the coin of sensitivity and specificity. Of all of the people who have the disease, those that get a positive test result will go into sensitivity, and those that get a negative test result will be counted as false negatives. Of all of those people that don't have the disease, those people that get a negative test result will be counted in specificity, but those people who get a positive test result will be counted in the false positive rate. Let's look at an example. In one study, the EPT pregnancy test had a sensitivity of 82% and a specificity of 75%. So of the women who were actually pregnant, 82% of them got a positive test result with the EPT pregnancy test. And of the women who were not pregnant, 75% of them got a negative result with the test. In this study, the women administered the test themselves. Interestingly, the sensitivity and specificity were higher with the same product in a different study in which the test was performed by a trained volunteer. According to data from the 2011-2013 National Survey of Family Growth, the rate of pregnancy is about 4% for women aged 15 to 45 in the United States. We can use this information along with the multiplication rule to find the probability distribution of the compound event of pregnancy status and test result. First, let's find the false positive and false negative rates. The false positive rate is just the opposite of specificity. So if 75% of the women who were not pregnant got a negative result, then 25% of them must have gotten a positive result, receiving an incorrect diagnosis from the pregnancy test. And the false negative rate is computed from the sensitivity. If 82% of the women who really were pregnant got a positive test result, then that means that 18% of the women who really were pregnant must have gotten a negative test result. Finally, if 4% of women in the United States are pregnant, then that must mean that 96% of women in the United States are not pregnant. Now we can apply the multiplication rule. So how can we find the proportion of women who are pregnant and have a positive test result? Well, we take the sensitivity, that is the proportion of women who get a positive test result, given that they really are pregnant, we multiply it by the proportion of women who really are pregnant. So we take 82% and multiply it by 4%, and that gives us 3.3%. So 3.3% of women are pregnant and get a positive test result. What about the proportion of women who are not pregnant and get a negative test result? Well, we take the proportion of women who get a negative test result, given that they are not pregnant, and then multiply it by the proportion of women who are not pregnant. So we take the sensitivity, 75%, and multiply it by the proportion of women who are not pregnant, 96%, and that gives us 72%. 72% of women are not pregnant and have a negative test result. So much for the women who get accurate answers. Now let's fill in the women who get inaccurate answers. Let's start with the proportion of women who are not pregnant but get a positive test result. So we take the false positive rate, that is the proportion of women who get a positive test result given that they are not pregnant, and multiply it by the proportion of women who are not pregnant. So we take 25% and multiply it by 96%, and that gives us 24%. 24% of women are not pregnant and yet get a positive test result. And finally, we have the women who are pregnant and yet get a negative test result. So we take the proportion of women who get a negative test result given that they are pregnant, that's the false negative rate, and multiply it by the proportion of women who are pregnant. So we take 18% and multiply it by 4%, and that gives us 0.7%. So 0.7% of women are pregnant and yet get a negative test result. Now we have the probability distribution of this compound event. It's the compound event of pregnancy status and test result. So there are 4 possible compound outcomes for this random phenomenon, and we have the probability associated with each of those outcomes. If we add up the 4 probabilities, we should come up with 100%. Well, 3.3 and 0.7 added together gives us 4. And 24 and 72 added gives us 96. So if we add 96 and 4, we do get 100%. So we do have a valid probability distribution for this compound random phenomenon. We'll come back to this example later. Sensitivity and specificity give two different kinds of answers to the question, how accurate is that medical test? Sensitivity talks about the accuracy for correctly catching people who have the disease, and specificity talks about the accuracy of not worrying people who don't have the disease. These two kinds of accuracy aren't necessarily the same for any given test. Just like we saw for the pregnancy test, the sensitivity and the specificity were not the same. Suppose I make a machine that flashes a red light if it thinks you have arachnophobia, and a green light if you are fearless in the presence of spiders. If I hardwire the machine so that it always flashes a red light, always claiming arachnophobia, it will perfectly diagnose everyone who actually has arachnophobia. The machine will have 100% sensitivity. That's great, but the machine will have terrible specificity, since it will get the diagnosis wrong for every single person who is fear-free. On the whole, most people would call my machine a failure at distinguishing people who have or don't have arachnophobia. Generally, we want our tests to have high sensitivity and high specificity, but it's often the case that sensitivity and specificity involve some kind of trade-off. If you try to increase the sensitivity, the specificity will go down, and vice versa. In any case, both the sensitivity and the specificity are necessary for getting a full picture of the quality of a diagnostic test.